video for lab number 8. Uploading now. Done uploading. Ignore how stretched out this cable is. Alright. Disconnecting my robot from the machine, or from the computer. Making sure my robot is prepped. Now I'm hitting button A. There will be the 2-second delay. With the green light on, we move until we get to the 80 centimeter mark. 40. Half again. Half again. And this dropped very much in line with the 6 centimeter mark. As you can see, the red light turned on. We're returning to the original position here. There, 120. If I hit button A, the green light starts. Continues on. And the red light turns on again, stopping right on the 5 centimeter mark. To examine the code, I'm going to scroll up here. We have our introduction to our project. We establish which parts of the robot we're using here. We define some magic numbers here, and some of the important variables in this function. We use some function prototypes because for us, Arduino kept giving us an error unless we had these function prototypes. In our void setup, we established our serial board, serial monitor, and turn on the specific pins we need for this project. This was an additional yellow LED. It turns on if we're detecting more than 100 centimeters of distance. This is because we were having a lot of trouble. My specific ultrasonic sensor only likes to work at an angle off the wall, and was giving us a bunch of weird inconsistencies. So this is just a quick check to say, hey, this is looking somewhat correct before we start. And when this yellow light is on, it works almost every single time. For a loop function, wait for button A. As soon as button A is clicked, we make sure that red LED is turned off if we're inside of a loop. And so the second time this is running, the red LED will already be on, and so this is to turn that off. Then we turn on the green LED, keep it on for 2 seconds, turn it off. We tell our robot to go straight. For the total distance it measures from the wall, minus 80 centimeters. So this will put us exactly at the 80 centimeter mark. From there, we enter a while loop. So while our distance from the wall is greater than 8 centimeters, we will pause for half a second and then move forward. Half the distance plus around 2.5 centimeters. This is to make sure we don't overshoot that 5 centimeter mark and we actually get a chance to hit it. I believe the minimum range for this ultrasonic is between 2 to 3 centimeters, and so we added these to make sure that we don't fall into that 2 centimeter limit. And then finally, once we are less than 8 centimeters from the wall, we turn on the red LED, and then we loop back up and we begin waiting for button A before we continue executing that code again. For functions, we have our basic calc pulse function, which measures the amount of pulses we need to go a certain distance. Our ramp to speed function gives us an acceleration. Gives us an acceleration curve. It should be a linear line, actually. A gradual increase in speed. Basically, if your left speed is less than your last target, then up it. If not, keep going. So this is our line to reduce overshooting. We did it all in one line to just try and keep it a little more compact. If we ever overshoot the target speed, This will set us back to the actual target. This is in case we have some weird increments or weird inputs in our parameters. This will make sure we reduce any error in our system. From there, it's pretty basic. If it's completed, it'll return the variable complete, because this function is a bool, and so you can put this in an if statement and say run this until it's done. And then here is just how we increment our speed. We use milli instead of delay, because this lets other code execute while this is running in case we need to do that. And then finally we've got void straight, pretty basic. We average the left speed and right speed you want in order to go straight, because with straight you want the speeds to be the same. The ideal speed of both wheels will be the same. Initializer encoder variables, we set a bool going forward and figure if we're going backwards or forward, because this function can do both. And then it uses the ramp speed function to ramp up the speed, and then continue on, and then we have a little bit of error correction here. It reduces our left speed or increases our right speed based on the error we find. Finally, once we're done with everything, we go ahead and set the speed to 0, and then we finish. The new function for this lab was our get distance function. Here we added a parameter called set. Set is just how many times you want a reading. Here we established a bunch of variables for use within this function. And in case you call it multiple times, this function just makes sure that everything inside of it is set to inside of the array we established here is set to 0, no matter the size of that array. The first thing we do is, for each time we need to take a reading, we send out a signal, wait 20 seconds. We turn it off, wait 20 microseconds, then turn it high, and then wait 10 microseconds. Then turn it off, and then we listen. And then we do the math to figure out how long this is going to be, and we divide by 58. This is a magic number defined up top. This gives us the distance in centimeters. If this is within the max and min values in the datasheet for our ultrasonic sensor, this gets added to our array. If not, we increment n, and n will skip it. N will, in the next following values, it'll go in and replace. It'll continue going in order without a missed number in our array, if that makes sense. Without this, you'd go like maybe 10 centimeters, 10 centimeters. Oh, you read 1 centimeter. We'd put a 0 there. This will make sure that the next value goes into that 0 slot. And then we added a longer microsecond delay here than usual, just because we're having some issues, and this seemed to help that. And then we have our bubble store algorithm. This is pretty basic. We found a guide online and follow it. It just, you give it the size of the array. You give it the size of the array, and then you compare the first element to the element afterwards, and if that is in the correct order, you continue to the next one. So you do the second and third, so on and so forth. And if you get through the entire set, you know that everything is in the correct order. If you didn't have to swap when you go through the entire set. And so this algorithm in particular just goes through it for the number of elements that you have in the set. If you go through it that amount of times, you know for sure that this has worked. And so that's what this swapped equals false variable is. It just checks if any time it has to swap, it'll switch it true and then do the swap. And so as soon as it goes through the full number of times, we know that this is completely sorted. And then finally, our median is found using this. If it's n, we divide by 2. I forget what this is called. But we get the remainder using this when you divide by 2. And so if the remainder is 1, we know this is an odd sized array, and so you can just grab the middle value. And if the remainder is 0, we know this is an even sized array, and you just grab the 2 middle values, divide by 2, and that's your median. And then our return for this whole get distance function is the median. gets us the median of that array. And so that gives us a quote-unquote average value from our set measurements.